Yes, so sorry for the delay. Let's start. So, uh, first I want to ask, do you have any questions about the last times? Okay, so let me remind what was the main formula we obtained and used. It was a homomorphic word identity. Which tells us that infinitesimal variation of some field sitting at point W is given by the contour integral around this point. Oh. And for example, so it was local. And there was also a global version of this word identity that tells that if epsilon of z some global transformation, then sum of such objects is 0. And we used this for conformal transformations, namely so if if it is conformal transformation, then this epsilon of z can be 1 z z squared. In this case, this global transformations give us 3 constraints on the correlator, like So we then use this and this constraints to check that correlator of a single operator is non-zero only when this operator is an identity operator, or at least its dimension is 0. A correlator of two operators is non-zero when their dimensions coincide. And in principle, it is clear that there are the three constraints, and we know that they are independent because well, it is first it is clear. Second, we can compute some determinant and see that it's non-vanishing. Also, we saw that in this case, these constraints are satisfied only in the case when there is some condition delta. So in principle, we know that they should that if we apply them for the 3-point case, they should fix a functional dependence of this correlator completely. And since we know that it will be fixed, we can just try to write it using this Bergman kernel. So, so we want to construct a correlator of these three fields. Let us multiply it by corresponding differentials of weight delta 1, delta 2, delta 3. So we know that this should be some invariant object because these fields transform as differential forms of this weight. And we know one object which is invariant. It is dz dw over z minus w squared. Bergman kernel. So let us try to construct this correlator in terms of this kernel. So, namely, let us write something like dz1, dz2 to some power divided by, so let's call it c1, or maybe c1 over 2, c1 minus c2 to c1. dz2 dz3 to c, well, maybe not bad notation, it's kind of c3, c1 over 2. And now I see that there are this disease in the denominator, and we need to adjust these coefficients so that they coincide with delta 1, delta 2, delta 3. So let us try to guess such coefficients. Namely, I'll try to write the answer immediately. So let us try something like this. Delta 1 plus delta 2 minus delta 3. So it should be symmetric in Z1 and Z2, so it should be some sum. And the Z3 should appear with some other coefficient. And also sum of all these coefficients should be delta 1 plus delta 2 plus delta 3. So let us try on this choice. And now check if it is actually working or not. So what are the coefficient? What is the power of dz1? On this and this. Delta 1 over 2 plus delta 2 minus delta 3, delta 1 over 2 plus delta 3 minus delta 2 over 2. So you see that it cancels in this case and actually gives this power. And everything else is cyclically symmetric. So the correct answer for this for these coefficients, and we can write them in the denominator as well. So and also, if we normalize a two-point function by a delta Kronecker, it means that we used almost all freedom in the definitions of this field, and maybe up some sign, and it means that this remaining 3-point correlator should be proportional to some number which cannot be removed by rescalings. So there is some 3-point function which is some data that describes this particular CFT, because these answers are universal, but for a 3-point function, the only universal part is its functional dependence on z1, z2, z3, and the overall coefficient is a parameter of theory. So far we know that one parameter of CFT is the set of dimensions of the operators which are present in this theory. Then another parameter is a set of this structure constants. So But it's not all. I hope we will see today that there is another parameter called central charge, which is denoted by small c. So, are there any questions about this formula? Hmm? Oh, we can, but we can perform some linear transformations on the space of fields, and since it is a bilinear form on the space of fields, this yes, and these coefficients are transformed as bilinear form, we can put it to a canonical form. So canonical form of bilinear form is so if you work with complex numbers, it's just identity matrix. So, in principle, there can be some states which are orthogonal to everything, have zero norm, and so on. But when people study unitary CFT, they usually say that the states are identically equal to zero. So. So in principle, we can consider something with such states, like some parts of CFT are still well defined. But if it is something physical, then usually people say that we just factorize by them, so they are identically zero. So. So after we do this, in principle, if there are fields with the same dimensions, there is an orthogonal group acting on them. And in this case, we can also diagonalize some other operator. Like if there is some charge or some parity operator, we can also diagonalize it. And this way fix this field and also this 3-point functions. But in general, the point is that these 3-point functions are some continuous parameter of theory. But nevertheless, usually it happens so that they can be fixed based on some global properties of correlators. It's called bootstrap technique or conformal bootstrap, which allows also to fix these functions starting just from the set of dimensions and on some a kind of physical definition of a theory. And they almost always have similar expressions, like some ratios of double gamma functions. The main example where these functions are computed is the Liouville theory, but for some reason they look similar in I think almost in all known cases. So there exist some exact formulas. Probably we will talk about this at some moment. Have time. So. So usually, even if they have some freedom, then it is something finite dimensional. It's not like we can take arbitrary set of functions and it will define a reasonable CFT. By the way, it is the point where sometimes it is important to remember that there is also anti-homomorphic part of CFT. And this is important precisely for this three-point constants, because when we compute something like this, then it is just some multi-valued function of z1, z2, z3. But in reality, so this formula should contain also some complex conjugate. So in reality, this formula will contain complex conjugate, which can make this function not homomorphic, but single valued. Okay. There is also a remark about fields at infinity, because here we place them at the finite points. But in principle, we saw an example when we compute some correlator which has this form, but with just z1, z2. And we studied what happens at infinity, and discovered some field sitting there. So there is a well-defined object called a field at infinity, which is defined like this. O delta of infinity is by definition r to the power 2 delta of r, well, limit when r goes to infinity. And we can check that it is actually something well defined. So, for example, let us compute the correlator of all of z with all of infinity. So it will be r to power delta to delta, or delta of z, r to power 2 delta. 1 over z minus maybe z minus r to power 2 delta. I will neglect all possible roots of unity, because in principle it should be multiplied by anti-homomorphic correlator. So I will forget about this. So it is just so it is delta 1, delta 2, delta 1, delta 2. So it does not depend on z, of course, and equals to this quadratic form on the space of fields. Now let us take this formula. Maybe it's better to write it in this direction. So z minus w, or maybe let us use notation z1, z2. So again, when you take this two terms, delta 1, delta 2 cancel. The R2 minus 2 delta 3 cancels this. So after all, it is in infinity. It is z1 minus z2 to power delta 3 minus delta 1 minus delta 2. So so it looks like I forgot this starchy constant. So it looks like the point correlator written here, but dimensions of these fields are related to power of z1 minus z2 in a different way. And if you try to perform some conformal transformation that would take this point infinity to some finite domain, we will see also these other prefactors. Here they disappear because of this definition. Mm. And you can also check what happens when we substitute some field with dimension 0. So a field with dimension 0 is the identity operator. It is, well, there can be some exotic topological theories when there are more fields with dimension 0, but usually it is just identity operator. So if it is identity, then this will disappear from the correlator, and we will see the usual formula. So also there is a constraint that this three-point function will vanish when one of well, this three-point function should turn into a delta chronica. One of these dimensions is 0, something like. So, are there questions about this? Okay, so this way we can fix 1, 2, and 3-point correlators, and they are universal in their functional dependence is universal in any CFT. And what about 4-point correlator? And by the way, this can be easily understood why their dependence is universal. using the fact that global conformal transformations can be used to put arbitrary 3 points to 0, 1, and infinity. And if we have, for example, 4 points, then then 4 points can be put to 0, 1, infinity, and some point t, which is called the anharmonic ratio of original coordinates. It is invariant under conformal transformations, and we can write a formula. So if we got the notation, it's probably something like this. We write some expression which gives t on the set 0, t1, and infinity. So there's something like z2 minus z1 z4 minus z3 in the numerator, and in the denominator we should swap two of these coordinates, z3 minus z1 z4 minus 4 minus z2. Let us check that it actually gives t. So here it is t minus 0 over 3 minus 0. And here is kind of something big, r over r. Oh, sorry, 1 minus 0. So it is actually t. And so it is clear that this anharmonic ratio is invariant under shifts, under simultaneous scaling, and also it is more or less clear than, that if we take inversion, like take inverse of all this, it will still be invariant, because both denominator and numerator produce a factor like z1, z2, z3, and z4. So in general, correlator of 4 fields will be some prefactor of zi minus zj to some power. which can be computed from this global conformal word identities, or it can be obtained by conformal transformation from this situation to the arbitrary position of points times some function of harmonic ratio. And And the non-trivial statement, which we will understand, is the following: that this function does not contain any other data except, well, there will be also the central charge, but in general, it will not contain the new data. It will only depend on dimensions and the structure constants. So all the data which describes the CFT is the set of dimensions, a central charge, and the set of the structure constants. And this can be computed using some algebra. And so this function will now depend on theory, but it will still contain a huge universal parts which are called conformal blocks. So, hmm? For the 4 points. Uh, oh, of course, you can have, I don't know how many harmonic ratios, maybe 6, because the easiest way to define it is to say that, okay, we have this 4 points, let us send the 3 of them to 0, 1, and infinity, and the position of the 4th point will be the anharmonic ratio, right? But in this procedure, we have some arbitrariness. We choose which 3 points to send to 0, 1, and infinity. And first, we can exchange these points, and second, we can also exchange t with one of these points. And as a result, possible harmonic ratios are something like t 1 minus t over 1 minus t, or well, t inverse, of course. Something maybe 1 over 1 minus t, something like this. So there is a permutation group of 3 elements acting on these anharmonic ratios. So there are only there is only 3 because of the following thing. Because if we have points 0, 1, 0, t1, and infinity, they map to themselves as a set. By the map, so this map maps 0 to t. So 0 to t, 1 t to 0, 1 to infinity, infinity to 1. So it permutes these points, like permutes two pairs of them, but preserves the harmonic ratio. So in principle, we could expect for we could expect to have more symmetries, but actually we can send any point to this extra one, which is different from 0, 1 and infinity, and then only permute 0, 1 and infinity, which gives this group as 3. So these quantities are harmonic ratios for different permutations of points. And if you want to write what kind of ratio it is, then it's easy. You should just write something that equals to, for example, this one should equal to 1 minus t on this configuration. It is so Z3 is 1. Z2 is t. So the first factor should be Z3 minus Z1. Here there is only one option, Z4 minus Z2. And here we would like to write another Z4 minus something. And here in the denominator, we want to have 1 minus 0. So that it is 1 minus t and not 1 minus t over t, for example. So it should be Z3 minus, sorry. It is 3 minus Z2, because it should be 1 minus t. So this is Z4 minus Z1. So here it is Z3 minus Z1, Z4 minus Z2. So is it clear? And of course, you can, so it works for this configuration of points, but you can check that 1 minus this and harmonic ratio will give this harmonic ratio. Maybe it's not. So it's. No, I wouldn't say that it is just some obvious computation, but it's always easier to think that your points are in this position because everything is so to C invariant. And if you have more points, then of course you can have more harmonic ratios, which just reflects on the fact that if there are 5 points, you can send 3 of them to 0, 1, and infinity, and fourth and fifth will go somewhere. And they will be two non-trivial harmonic ratios. Okay, so is that okay? Yeah. Now, now let us change the topic a little bit and go back to this homomorphic word identity. So we see the following phenomenon that formula on the left-hand side is some action of some generator on a field. It produces some new field, and when it was some symmetry which we knew originally, we knew precisely what is this transformation. And on the right hand side, we have some object of the following kind. We take one field in a CFT, multiply it by some function, and integrate around another field. And in principle, we can take this as the definition of the action on the space of fields. So actually, I don't actually know what to tell first. Let us let us actually think about this algebra structure. So, I think let me maybe first introduce the action of modes of this field, because it is much more useful for some computations. So suppose that a field J has dimension delta. Then and this dimension so usually it is integer. So, for example, so what was the dimension of U1 current, and what was the dimension of the energy momentum tensor? Yes. So we define now the action of modes in the following way. So Jn of W is by definition integral around W d z to power dz over z z minus W to power delta plus n minus 1 times j of W all of j of z all of W. So the question is, what is now the physical dimension of this symbol Jn? So if dimension of O was some delta O, then what is the dimension of Jn O? So dimension of Z is minus 1 because it is a length scale. And dimensions of fields are positive. Hmm? Z minus W delta, but it should cancel with the dimension of J. Yes, yes. Then the minus 1 cancels with Z. So I have delta O plus N. Minus N, yes. So this is the motivation for this definition, that now we don't need to remember dimension of this current. And so dimensions of its modes depend only on their indices. So we just define some action in the space of fields. It is some operator which is constructed in this way. Like we take our original operator and insert some defect around it, insert some integral around very small circle. And if we compare it with previous studies, it corresponds to a transformation with a special form of epsilon. So it is epsilon of z chosen in this special way. So when n is negative, it is something singular. So when, in a sense, when it is sufficiently negative, but when it is positive, this transformation is regular, and if it is high enough, then it can start vanishing, because product of two fields cannot contain arbitrary singularities, and also because of this argument, because if we take mm, if we go to some higher ends, we can get fields of negative dimensions, which are usually excluded. Oh, but now we just define this abstract object. So the action of Jn on O. Mm. We can also formulate it in a different way. So we can say that if we want to compute this integral, then we need to expand the j of z with O of w around z equals to w. And this integral says that coefficients of expansion are given precisely by Jn of O. So this definition can go in the opposite direction. So that J of z O of w is sum over n greater than like this. So it's another way to write the same statement, the same definition. So and by the way, I don't remember if I told this, but such formulas are called OPs, or operator product expansion. So for the moment, we are just using them, and I do not explain how to how to understand that they should exist in CFT, but not necessarily in the general theory. And we will discuss it later in more detail. But in principle, it is more or less clear then that if some function is holomorphic, then it is also analytic, so we can expand it as a series, and then when we sum this series, we will get back our original function. Which is not true for arbitrary smooth functions. So, so one argument why this exists is homomorphicity of all objects. So, but there are also more physical arguments. But for the moment, let us just suppose that there is such equality which holds under the correlators. And this equality defines as some new fields. And so there is some action on the space of fields which comes from generators of some symmetries. And let us try to compute the algebra generated by these actions, because we know that if we have some transformations, we can then they form a group, and infinitesimal forms of transformations form some algebra. So it exists on the left-hand side of this formula. So there are some transformations of fields, and on the right hand side we have some definition which does not know about classical symmetries. It is just defined in the quantum theory. So we have some short currents, and they generate this new fields Jn of O. So let us try to compute what is the commutator of such transformations that come from the field theory. So the question is, if you have some currents J1 maybe let us call them J and some I. Jn, some Im, so I want to compute this. So let us try to do this. So take some field, for example, at point 0. It doesn't matter because we can shift coordinates. So it will be O of 0. And here we act with first with Im, which means that we integrate around some small circle, some small contour around on this field. This is I of z, for example. And then when we compute this expansion, we act with another generator with j. So I of z, we act with j of w. Is one action. So we can kind of insert these two shells around this operator. So if it was something multidimensional, they would be two spheres containing this operator inside. So here we first act with I, and then act with j. So this will be I. So it will be j to the right. It will be jm in O of zr. And if you now act in the opposite order, it will be j of w here of z. and we want to compute their difference. So this difference will be a kind of the same integral, but around different contours. So here it will be the integral. So the first integral is along the contour when absolute value of z is less than absolute value of w. And the second integral is around the contour when absolute value of w is greater than is less than absolute value of z. So, and absolute value of z equals some constant. So one constant, another constant. So and here it is dz dw z to power delta I plus n minus 1 w to the power delta j plus m minus 1 times I of z and j of w all of 0. And now there is some standard argument that if we want to compute this this commutator, we need to try to pull one shell through the other one. So let us, so here we, for example, let us try to do this with this one. So we want to pull this integration contour through this one to make this integrals the same. So, so there is no color chalk. So we want to do something like this. Pull this. So choose some contour here. Pull this one. Pull the outer contour to the inner one. So it can be done at a fixed value of z. So in the sense that this internal current stays at some point, and for each such point, we need to pull the outer contour inside. And so final result will be this relative position of the contours. So this will cancel, and the only contribution which we get is the contribution coming from a possible pole between z and w. So it looks like, so if I draw some local picture, then it will look like this at the very last stage, and the final transformation is to pull this and to compute this integral around point z. So this picture looks like this. So we have integral around z. We have integral in z around 0, and integral in w turns into the integral around z. So is it clear? And also the same happens in higher dimensions, because in that case we will have some integral of one field over one sphere. We will have some outer sphere that can be deformed inside the inner one, and the only contribution which appears during this process is a contribution from some small bubble around this field which lives on the inner sphere. So so this bubble is drawn here, like. And we can kind of separate it into two parts. So originally it was the integral like this, but this inner part was cancelled precisely by this integral. And we are left with just integral in z, in w around z. So we finally get the integral in z around 0. Oh, absolute value of z equals to constant. Here we have dz, and here we have integral in w, and this integral is around z, and it contains z to delta I plus n minus 1, w to delta j plus m minus 1, j of w, I of z. Acting on O of 1, or O of 0. So we can call we can now call this integral around z, which is just a function of z. We can call this the nu. We can call it a commutator of jn times jn times im. Also, or maybe we can say that this is this is. Oh, maybe I will not write any other definitions at the moment. Mm, I just want to say that that uh, this commutator of two actions expressed in very similar form to original action. We have some field that depends on a point z. It is multiplied by something and integrated around this point O. So um, there is a hope, for example, that this algebra that we will get some closed algebra of operators on the space of fields. And a result of this computation depends on the OP of J of W and I of Z. On the singular part of this OPE. So is it clear or only on the singular part? Mm-hmm. Mm-hmm. Hmm? Oh, no. In what sense it doesn't see I? We obtained some new operator, which is defined as original operator plus some defect inserted around this, and it should be made as small as possible because our operator is some operator sitting on the point. And then we take this construction, act on it with I. So I acts on this with J. J acts on the space of all possible operators, and is including this one. So we write this. So we have this bubble around first I bubble around O, and then a bigger J bubble around this compound object. And here we do this the same in the opposite direction. So what is the question? Yes. Mm. Yeah. Oh, but in what sense it doesn't see it? This correction, delta correction, depends only on the dimension of the field we are inserting. So. But wait, it depends on dimension of I only. Oh, what is the question? So this shift of mode is a function of this particular operator, which I. Mm. And but in general, they of course see each other when we try to pull this bubbles through each other. We need to write a term when we move. inner field through the bubble formed by the outer field, or vice versa. Um, so, other questions? So now let us try to apply this for the symmetry we know. Namely, let us say that this J is a U1 current that corresponds to translation symmetry. Okay, probably can erase this. So let me remind how we compute correlators, including this J's. So, for example, if we want to compute a correlator of some J of Z, J of W, J of Z1, J of Zn, to N, so that is non-vanishing. Maybe not necessarily J's. We can put phi's or some other operators. So it does not really matter. So, such correlator is a sum over all possible pairings of contractions. So all these pairs of fields should be somehow connected. And each contraction is 1 over Z minus W squared. But we can notice that there are two different types of contraction. One contraction is when we contract J of Z and J of W. And everything else which is written there contracts to itself somehow. And another term is when J of Z is contracted to some of these fields, and J of W as well. What can we say about the behavior of these two terms? So, mhm. Yes. Uh, so so it is 1 over z minus w squared times this sum of all contractions. Oh, sum of these contractions plus sum of such contractions. Or something regular. Mm. So looking at this formula, we can, well, in principle, we can also define this regular term of expansion by saying that, well, we just need to give some name to it. So it is OP of J of Z, J of W is 1 over z minus W squared plus this object which can be either defined by this formula, or we can give it this technical definition that when we insert it under the correlator, we should not consider contractions between J of Z and J of W. So it's some new field of this form. And this symbol is called bosonic normal ordering. So now it can be understood just as in definition. So um, there is some operator that that is defined either as a difference of J of W, J of Z, J of W minus the singular part, or we can say it in this operational way that when you compute some correlators, we should not consider contractions. And it's actually not identically that normal ordering for the exponentials, but they are very close. They basically differ by some numeric prefactor. Okay, so we have this OP of J of Z and J of W. And let us try to compute the commutator of Jn Jm. Acting on O. Actually, I forgot 1 over 2 pi I in all these integrals. Maybe also there. No, I wrote it. So this will be the integral over dz over 2 pi I. Integral so it's around 0, it's around z to the n w to the m 1 over z minus w squared over 0. All right. So who knows what does this integral in w equal to? So this integral in dz stays. Oh, yes. Oh, pi I cancels. So and what is left? No, why? It stays at point 0, which is far from z and w. So the picture is there on the top. So we have a fixed value of z. 0 is always 0, and we integrate over a small contour around z. M plus n. Yes, thanks. So so concerning the order of obvious fact, z to m plus n minus 1 all of 0. Wait, let me check the order. So I'm using the order on the left hand side because it is correlator of GM with IN. So it is correlator JM, JN. No, that is fine. Okay, but how to compute the remaining integral? Yes, and when it is M. Mm-hmm. So we give, so it gives us delta n plus m 0 O of 0. So commutator of Jn and Jn equals to m delta m plus n 0. And this is called Heisenberg algebra. Right? What we see here that originally we had some classical symmetry, which was just shifting the field by some holomorphic function. But at the quantum level, this symmetry becomes centrally extended. So this right-hand side is called central extension. Because it is proportional to identity operator, which we can probably write here explicitly. So the operator which acts on all fields trivially. And this is purely a quantum effect, which comes from a non-trivial correlator of G of Z, G of W, which was computed from a quantum field theory, from the path integral, or from Schwinger-Dyson equation. So classically, we had nothing like this because there were just shifts of field by some functions. So there was no reason to have some non-commutativity. So are there any questions about this? Okay, so we have this algebra, but actually we have not only the algebra, we also have some natural representations of it, which are already in our theory. So, namely, Then let us remember what would the OP of J of Z. Let us remember what is the OP of J of Z with some V alpha of W. So who remembers this? Oh, but wait, the alpha is a field that transforms, so the alpha of W transforms to e to alpha A of Z, V alpha of W, under this symmetry that corresponds to the current J. And we also know that we also know homomorphic neutral theorem that well, let us put here epsilon g epsilon of W, the alpha of W equals to the integral dw over 2 pi I j of z or j of dz j of z epsilon of z the alpha of W. So how to combine these two statements and find the OP of the current with on this field? Well, alpha v times what? Because if it is just alpha v, if this OP is alpha v, then then the integral is regular and it vanishes. Yes. Yes. Plus regular. So we know this. It comes from the definition of this symmetry. And now let us take this definition of GNs. Let us just see what their values are. So it is a GN. So in principle, over all possible integers, GN the alpha of W over Z minus W to n plus 1. So we see that the highest pole is of order 1, which corresponds to the action of J0. So J0 acting on V alpha W is alpha, V alpha of W. and Jn with positive indices act just by zero, right? So we see something. We see how the half of these operators act. Mm. So mm, and now let us think about representations of this Heisenberg algebra in general. So do you know how to construct them? Yes, it's of course doable, but people don't care about this because you can have harmonic oscillators with different frequencies, with different commutators, so we can work with just original GNs. Mm. So. Uh, so it is a combination of J0, which commutes with everything, and yes, pairs of commuting harmonic oscillators. Jn with J minus n equals to n equals to n. So one of this so um, uh, so the highest rate representations of this algebra looks like this. So J0 is central, it commutes with everything. So J0 on acts on vacuum by some number alpha, which we see here. Jns with positive indices are annihilation operators greater than 0 by 0. And Jn with negative indices act by something. They produce some new vectors in this representation. So the space of this representation is a span of all the vectors of the form J minus how to write them, J minus 1 to n1, acting on alpha. J minus k to nk. So yeah, and this states can be labeled by the Young diagrams. Namely, we should write something like this. And k rows of length k nk minus 1 rows of some length k minus 1 and so on. We will see later that the number of boxes in this diagram has a very clear physical meaning, and that actually it is very natural to write this Hilbert space as a direct sum over states with a fixed number of boxes. We'll talk about this the next time. But what we definitely see at this moment is the following phenomenon, that we take just a single field, which is this exponential field, act on it with the symmetry algebra, and obtain some huge vector space, some infinite dimensional vector space of fields, which are constructed just from the original field and from the symmetry algebra. And this is a generic situation in CFT, in the sense that the space of fields is a direct sum of some infinite dimensional representations of some algebras of this kind. So it always contains Virasoro algebra, which we will study the next time, which comes from energy momentum tensor. But it can also contain some additional symmetry algebras, which are either simpler or more complicated than Virasoro algebra itself. So here we see that this U1 symmetry contains creates infinitely many fields, and we'll actually look at these fields. How they look like, because in principle it is clear how to write something like this in bosonic theory. At least we can write objects with the same with the same weight and the same numbers. Namely, we can write expressions like d j d k1j dj to n1 j to n1 probably j to n1 dj to n2 and so on dj to nk acting on v alpha. So this is some abstract action in some abstract space when with this OPs and so on. But in principle, if you want to write these fields explicitly as some fields that can be so it's dk minus 1 j, which can be put under the correlators, then we can write this basis. And And if you think about a generic field, then it is, I think, the only field which we can imagine, because we have exponential, which has some definite dimension. We can also combine it with some derivatives. In principle, we can put some j or derivative of j into the exponential, but if you compute correlators of such fields, you'll see some exponential of 1 over z minus w. So something that has essential singularity, and these fields can also be studied, but it is something more complicated. So maybe so they will correspond to coherent states of this Heisenberg algebra, like exponent of j minus exponent of j minus 1, minus 2, and so on. Okay, maybe that's all for today. Do you have any questions? Okay, thanks for your attention.